Okay, well, good morning, everyone. This is the fifth conference, I think, that we scheduled last time we were in lab, and that we agreed that we would have before spring break. Uh, so the topic of this conference is atomic theory development. Now, I definitely encourage you and remind you that these conferences are no replacement for your own independent reading. So you are expected to have read or be in the process of rereading atomic theory in the Tro book and in the OpenStax book, or the OpenStax book. And you'd be expected, as I'm sure you do, as any student would, have a look around on Google, on other platforms where you can just read around the subject, research the subject yourself. So I'm just going to point out some salient features, a minimum of what I would like you to know, what I would like you to come into Chem 101 with. Okay. So I'm going to summarize what we should know, and then we'll go back and then go into some detail. So we'll look at the end first. So to summarize, there are 5 models of the atom. And I'm going to draw it like an Olympic rings. Like the 5 rings of the Olympics. There are 5 models of the atom. So let's assume that these circles are really spheres, 3-dimensional models of the atom. Let's say this is the first model. Let's say that's the second model. Let's say that's the third, the fourth. The fifth is today. What we believe atoms are today. But this is a long story. This is, depending on how you count your history, it's several thousand years old. But let's use a more conservative view of history. Let's look at modern atomic theory development. And let's say it started around late 1700s, early 1800s. So let's say it started around 1800s. So just after the American Revolution, so that time period. Okay. So the first model is Dalton's atom. The model according to John Dalton, who was an English geologist, I believe. Then to go from Model 1 to Model 2 is accredited to Thompson. Notice there's no P in Thompson. So if you go online and you read that there's a P in Thompson, it's a typo and stop reading immediately. Okay, so to go from Dalton to Thompson, there's an experiment that we need to look at called Cathode Ray Tube experiment. We'll go back and look at a little bit of detail what that was. So Dalton to Thompson via the Cathode Ray Tube experiment. The third model of the atom is accredited to Ernest Rutherford. And the experiment that led to its discovery was the gold foil experiment. Gold foil experiment took us from the Thompson model of the atom to the Rutherford model of the atom. It's probably worth noting here that the Thompson model is often called the plum pudding model. for reasons that we'll go into, trivial reasons that we'll go into later. The Rutherford model is called the nuclear model. For reasons that we'll go into later. What led to the fourth model of the atom? Well, the fourth model of the atom is accredited to Niels Bohr. It's often called the planetary model. For reasons that we'll go into later, as I'm sure you've guessed by now. What led to that was quantum mechanics. So the discovery of a new type of physics called quantum mechanics led from a great shift from the nuclear model to the Bohr model. So models 1, 2, and 3 predate quantum mechanics, so they are therefore classical Newtonian mechanics. And then the fifth model which is not really accredited to one person, it's accredited to a movement of many people. Heisenberg, Schrödinger, Planck, Einstein, many people, Dirac, they're all contributed to this model. In general, it's called the wave mechanical model. Wave mechanical model is the current model. Why do we study the history? So I'm going to put quantum mechanics here again. Just further developments in quantum mechanics. Before we erase this and look at in some detail each one, why does a student not just spend all of his or her time looking at the wave mechanical model? The reason is there's a benefit to studying all of them because, in fact, throughout chemistry, although 5 is the proper model, it's very complicated, and sometimes we can get information by making some gross assumptions and using inferior models in different circumstances. So we don't always have to bother with the rigor of Model 5, and for that reason, students typically learn the other redundant models because they're actually still useful in many cases, especially at this level at Chem 65. So one of the things to look out for moving forward, one of the things that can make chemistry difficult is that a professor will sometimes be using Model 1, sometimes be using Model 3, sometimes be using Model 4. But the professor typically doesn't say, oh, by the way, I'm using Model 4. So the student constantly has to shift from thinking about chemistry from the perspective of Model 2 to thinking about chemistry from the perspective of a different model. And that's something that with experience that you would naturally do. But as you are acquiring that experience, it can be challenging. Okay. I would ask, are there any questions, but I don't believe anyone has joined us live yet. So again, if you do have questions and you're not able to join us live, then you can always go to the Gibbs Exam Worries discussion forum and you can post your questions there. And I can look at those during spring break also and get back to you as soon as I can. Okay. So with that, I'll erase the board and we'll go back and have a little look at the Dalton model. So the Dalton model of the atom, I've drawn it here as a circle, but if you appreciate it's a three-dimensional featureless, oh no, is there an E in featureless? I think there is. Featureless. I don't think there is. I've changed my mind. If there is, I'm sorry. So it's a three-dimensional featureless sphere. So why a sphere? Well, Dalton imagined that everything was made of small units that couldn't be subdivided. So different objects in the natural world were just different amounts of these indivisible, indestructible units packaged together. Why a sphere? Well, the math is simplest for a sphere. You know, why not a square? Why not a cube? So the world is not made up of cubes. Atoms are not cubic. For example, the math that describes this region would be different than the math that describes this region. So if you've got corners, they're mathematically distinct. So that would be more complicated and therefore less likely. So spheres are very simple. They're described by simple math. And so if you take the center, the math that describes any part of the exterior is the same. If you take the center here, the math that describes that would be different than the math that describes that, would be different than the math that describes that. So spheres are simple. So he chose spheres. He had no proof. He just chose it, and it was a logical choice. So that's all there is really to say about the Dalton model. It's the simplest. It just says that everything's made up of small units, and they're indestructible. They're featureless and indestructible. Later came Thompson. So remember, Dalton was 1800s, mid 1800s. Thompson was late 1800s. So they would have been a different generation, but alive at the same time. So around the late 1800s, early 1900s, this is when Thompson realized that he took Dalton's model and he did his cathode ray tube experiment, and he found out that there were electrons inside. So originally he called them cathode rays, but later it was realized that cathode rays are electrons. So it was Michael Faraday that was studying electrons. Thomson was looking at these things from a cathode and he called them a cathode ray. It was later on that it was realized that they were looking at the same thing, so cathode rays were electrons. So it just adds one feature to the Thompson model, and that feature are electrons. So let's have a quick look at the cathode ray tube experiment. The cathode ray tube experiment. So basically, you can look at diagrams yourself online or in the textbook. So basically, Thomson took a tube and he pumped out all the gas molecules from the tube, or the vast majority of them, and he put two plates inside the tube with opposite charges, so a positive charge and a negative charge. And the positive plate is called the cathode, and the negative plate is called the anode. He then, well, to generate this, he connected it to a source of voltage, and he pumped voltage across this to generate the difference in voltage. And he noticed that when he set up a difference in the voltage, he noticed that apparent rays of light would come, and they would strike either a plate here or a phosphorescent screen, but they were being attracted to the anode. And he could see a spark of light, trail of light with a flash of light at the end. Okay. So he noticed when he put field orthogonal to the flow of cathode rays, so let's say he put a magnetic field here or another electric field, he noticed that he could deflect the ray towards the positive plate. So wherever this ray was, it originated at the cathode. So this cathode ray, he knew, was negatively charged because it was attracted to a positive plate. So he knew that opposite charges attracted, and he knew it was attracted to a positively charged plate. So the thing that was being attracted had to be negatively charged. He changed the material that he constructed the cathode out of, and it didn't matter what material he chose, he always saw this cathode ray. So he made an assumption that wherever the cathode ray was made of, regardless of what it was made of, it contained cathode rays. Wherever the cathode was made of, it contained cathode rays. So these cathode rays were ubiquitous to any material. That was his assumption. It wasn't just any particular material. They were ubiquitous to all materials. Nowadays, we know that indeed electrons are ubiquitous to all atoms. Okay, let's have a look at what he did. So this is roughly what it looks like. Let's have a look at what it does. What does the cathode ray tube do? It gives the ratio of charge to mass of the cathode ray, which we now know as the electron. So his experiment gave the charge of the electron divided by the mass of the electron as a ratio. So what it doesn't give the charge or the mass, it gives a ratio of the two. So alone, it's incomplete. Alone, it won't tell you the charge or the mass, it will just give the ratio of the two things that you don't actually know. So another experiment was needed to either identify the charge or the mass, combine it with this to give both the charge and the mass separately. And we'll come to that in a minute. So let's see how we get the charge and the mass here. So we're going to have a cathode ray hitting a positively charged plate and being reflected by a negatively charged plate. And we're interested in this deflection, we'll call it S. So we're interested in that reflection we'll call S. Light's annoying, I can see it right now. Okay, so we're interested in that reflection called S. We also want the length that we've traveled. And we'll call that L. Now, length is the speed times by the time of travel. So length is actually the velocity of the cathode ray multiplied by the time it's actually traveled for. So we'll call that delta t, where delta t is the final time minus the initial time. So the start time, let's say, is t1, and the time it takes to get here is t2. So the delta t is t2 minus t1. So it's numerically equal to t2. Okay. The velocity, he could measure the velocity of the cathode ray because he knew from Maxwellian mechanics that the velocity of an object in an electromagnetic field is just the ratio of the electric field E over the magnetic field B. So he was able to combine these two equations, insert E over B into V here, and figure out that the length of travel is just the ratio of electric field and magnetic field times by the time of travel. So he was able to measure the length, he knew this, and he could measure the time. So everything here was measurable. Well, this implies that the time of travel is just equal to, if we take the B upstairs and the E downstairs, it's just the length of travel multiplied by the ratio of the magnetic field over the electric field. Okay. Now, from kinematic equations, which we won't derive because it would be more than a Chem 65 would request. But I'm just going to state one of the conclusions from the kinematic equations. So if you're familiar with them from physics, that's great. If you're not, no worries. So from kinematic considerations, we know that this deflection S over here is equal to the acceleration of the cathode ray times by the time of flight squared over 2. We also know from Newton's second law that force is mass times acceleration. So this implies that the deflection distance here, S, if we replace A with F divided by M, then this equals F divided by M, but there's also a 2 down here, so it's 2M multiplied by the time of flight squared. Now, F is force, so it would be appropriate to narrow down what type of force we're dealing with. We're dealing with electric force, or the force of the electric field, which is the force on the electron as it travels. So we know that the force of the electric field is the charge on the electron times by the size of the electric field. Well, this implies if we replace Fe in here, and therefore replace Fe with Ee, this implies that the deflection here, S, is the charge on the electron E, the electric field capital E over 2m multiplied by the time of flight squared. So if you compare this equation here with this equation, all we've done, we've relabeled variables according to the scratch work over here. So what we're going to do now, we're going to sub in delta t squared from over here. So it's going to be L squared B squared over E squared. So we have S equals E. Now this E cancels this E here, because when we substitute in delta t squared, we have one E in the denominator. So one of those E's will cancel the numerator E here, and we'll be left with one extra denominator E. So it's E L squared E squared over 2ME. So if you take a second or two to do some plugging in of delta t into this equation, you'll quickly arrive at this equation. Or if we want the charge to mass ratio, which we said that that's what Thompson gives you, the charge of the electron divided by the mass of the electron. So we take 2me up here. Sorry, we take 2e up here. We want to keep m where it is, don't we? So it's 2se over L squared D squared. So this is what Thompson did. He got the ratio of the charge of the electron to the mass of the electron. And numerically, it's equal to 1.76 by 10 to the 11. And the units are coulomb per kilogram. Kilogram is a unit of mass. Coulomb is the unit of charge. We have the ratio of the unit. We have the ratio of the charge to mass. Do I expect you to produce this in an exam in Chem 65? Absolutely not. Would I request that you spend a few minutes studying it so that eventually, when you do have to know this in a subsequent class, it's not the first time you've seen it. So I would expect that you can follow this if it was written in front of you and explain it in a casual conversation to somebody else. So again, Thompson gave us the ratio of charge to mass. Let's now move on to something that was needed in addition to this to help get the charge and the mass separately. So we're going to look at Millikens oil drop experiment. So again, please do a little bit of reading about this. I'm just going to give you some of the salient features. So again, we know from Newton's second law that force is mass times acceleration. Now, the specific acceleration of interest here is acceleration due to gravity. So we're going to say this is the mass of an object accelerating due to gravity, g. We've just seen previously that the force on the electron, because of the electric field E, is the charge on the electron multiplied by the electric field. By analogy, we're going to say that the charge on an electric field times by the electric field itself, sorry, the charge on the electron by the electric field E equals mg, which implies that the charge on electron over the mass of electron is acceleration due to gravity over the electric field. So this is a link to the previous calculation we've just seen. So Millikan wanted to look at the charge. So he knew that the charge was just mass times gravitation, which is force, divided by the electric field. And this is the electric charge. This is numerically equal to 1.609. It's negative. It's a negative charge by 10 to the negative 19 coulombs. Okay. So Thompson had an equation and a numerical value for the ratio of charge to mass. Millikan around the same time came up with a different experiment that you can have a look at yourself. And he ultimately found out the charge on the electron as negative 1.609 by 10 to the negative 19 coulombs. So to summarize, if we combine those two together, Thompson gave us the charge to mass. Millikan gave us the charge, so let's take the reciprocal of the charge. If you've got the charge to mass and I've got the charge, then we can ultimately get the mass. So we'll get 1 over the mass originally, but you can quickly isolate one of the variables from the other. So together, we now have the mass of the electron and the charge of the electron separately. So now we're in business. Okay, I'm going to erase the board and then we will move on to the Rutherford model of the atom. So Rutherford was the third model of the atom and the last classical mechanics model of the atom. So Thompson took Dalton and added a feature found from an experiment. Rutherford took Dalton and added a feature found from an experiment. So we're going to start with Thompson, which was a sphere with electrons in it. And Rutherford just contributed the positive nucleus. So that's why it's called the nuclear model, because he identified a region right at the center that was the nucleus. He found that the nucleus had a high density. So we know that density is mass per unit volume, and the nucleus has a high density. What does that mean? It means it has a large mass over a very, very small volume. How did he come to that conclusion? He came to that conclusion from the gold foil experiment. So let's have a quick look at the gold foil experiment. And there's some nice details and illustrations in the PowerPoint slides that are available to you on Canvas. But in essence, he took a source of alpha radiation and he focused a beam of alpha particles at a piece of gold foil. Let's say the gold foil, it wasn't exactly a single layer of atoms, but it was thin. It was thin. Why did he use gold? It was commercially available and it could be machined into a very thin sheet. It was actually lucky that he chose gold because it just so happens gold has got a very large nucleus. So he was trying to discover something that happened to be large. Had he chosen aluminum foil, he probably would have been unsuccessful because aluminum has a relatively small nucleus. He would have missed it. So he noticed that when he fired alpha particles at a thin piece of gold foil, the alpha particles went right through. And he had a big screen, and he could see that the passage went right through because it would hit a screen, and he could see a beam of light. This could be a phosphorescent screen that would spark as light when something hit it. Very, very rarely, so let's say about 99% went right through. But very, very rarely he would hit the side of something and he'd have a different angle. And almost never, so this screen was more of a wraparound screen. Even rarer still, he would hit something more head-on and it would reflect back a much harsher angle. This is how he concluded whatever it was very small because it was very hard to hit. He concluded it had a high density, in other words, a very large mass per unit volume, because when he did hit it, it never moved. He bounced off with his alpha particle. So wherever it was much bigger in terms of mass than an alpha particle. And he knew that an alpha particle was much more dense than an electron. So we knew that this wasn't electrons. Anyway, it took him about 2 years to come up with this conclusion that there was something at the center that must have been positively charged because alpha particles are positively charged. So he knew that it was repelling the alpha particles somehow. And it was very massive. Okay. So you can have a little bit of a read around that yourself. Okay. Now, around this time, around the turn of the 20th century, so about 1900, there was a revolution in physics happening, the quantum revolution. Basically, as atomic theory was gaining popularity, scientists realized that classical mechanics, which is based on Newtonian mechanics, is incapable of explaining atoms. Okay. So here's the problem. So remember, classical mechanics, this is up to Rutherford. So if you consider the Rutherford atom, you've got an electron from Thompson's model, but now you've got the nucleus from Rutherford's model. Well, it was known that opposite charges attract according to Coulomb's law. So what should happen, similar to water going down a drain hole, you know, the water would circulate around the drain hole, it wouldn't just go right in. So this attraction between opposite charges should lead to an acceleration of the electron, and ultimately, over time, matter would disappear. So if the size of the atom is based on the distance of the valence electrons from the nucleus, We saw that in the conference yesterday when we looked at periodic trends. If the world that we see, the universe that we see around us, has a finite size, it's because it's made of things that have a finite size. They have a finite radius. But classical mechanics doesn't explain where the size of the universe comes from. It says that the universe should have no size. So that was the nail in the coffin, so to speak, of classical mechanics in terms of chemistry. So this would be a catastrophe. So somehow we had to stop the electron doing this, and this is where Bohr came in. So Bohr was looking for an example that existed where there was a stable orbit, so we looked at the planets. It's known that the solar system is stable because the planets have a fixed orbit. So he said, what about having a nucleus and have the electrons going around in orbits? So let's call this the first orbit, n equals 1, n equals 2, n equals 3, n equals 4. So n1 equals the first orbit, n2 is the second orbit, etc. So like layers of an onion or train tracks around the city, how do you stop the trains crashing into the city? Put them on tracks so they can't move. So he said, okay, electrons can jump between orbits, but they can't jump. They must land on an orbit. They can't land in the middle of nowhere. So you can transition up and down, but you can't land in the middle of nowhere. So you're either on the orbit or you're nowhere. This transition we'll look at in more detail in chapter 9. So after the Gibbs exam, when we start looking at the chapter 9 is an introduction to quantum mechanics. So we won't go into too much detail about what these transitions are just yet. Just to know that the presence of orbits now stabilizes the atom. The atom can't just smash into the nucleus. So it preserves. So the Bohr model of the success is it preserves the radius r of matter. The universe now has a finite size and it agrees with what we see. This idea of a quantity, so either quantity 1 or quantity 2, so these are quantities this is where quantum came from. Quantum mechanics is the mechanics of quantities of energy. So this was the birth of quantum mechanics, and this was around 1900. But we'll look at more detail in chapter 9. So from about 1926 to today, we have the wave mechanical model. So basically, we know that electrons exist in not orbits, but orbitals. So we can have s orbitals, p orbitals, d orbitals, and f orbitals. Now you'll probably recognize these letters from the periodic table. These are the blocks in the periodic table. So when we were looking at periodic trends in the last conference, we were looking at the S block, the P block, the D block, and the F block. Exactly analogously, these are the residences of S electrons, P electrons, D electrons, and F electrons. And when I say S electrons, I mean electrons in S orbitals. When I say P electrons, I mean electrons in P orbitals. D electrons are electrons in D orbitals, etc. And again, we'll go into a little bit more detail about that when we discuss Chapter 9 in preparation for the Curie exam, which will be after the Gibbs exam. So the electron can exist inside orbitals. So how do we draw this? We basically give it a dashed line and we say 95% probability. So you'll see when we study Chapter 9 that the structure of the atom is complicated and it's governed by new quantum mechanics, which is an indeterministic concept. So because of indeterminacy, we have probability. So it's not 100% because of something called Heisenberg's uncertainty principle. And we'll talk a little bit more about Heisenberg's uncertainty principle in the next, well, not in the next conference, but when we look at Chapter 9. We know the S, P, D, and F orbitals are in there, and we know that the electrons are in those orbitals with about 95% probability. So that means the electrons can be outside with about 5% probability. A big aha that I'll point out to you, the wave mechanical model is the periodic table. So we'll convince each other that actually the periodic table that you have in every single exam is a gateway into understanding what this wave mechanical model really is, because it's actually the same thing. So it's a very elegant table, it's packed full of information. Not only does it summarize the relationships of all the elements, it itself encodes the actual structure of every single element. So that's one of our jobs, is to try and decode some of the information in the periodic table. Okay, so are there any questions concerning anything we've looked at? If so, if you could send a chat now. If not, or if you have a question and you're watching this as a recording, you can send your questions to the discussion forum called Gibbs Exam Worries. It's on the Canvas site. And again, I'll be looking at that daily over spring break. Now, I'm actually at a conference in San Francisco, so I won't be able to look at it every hour. But a couple of times a day, I'll try and look at it in the morning, maybe throughout the day once, and maybe at the end of the day. But worst case scenario, at least once a day. So hearing and seeing no questions, I'm going to close the conference. So have a good spring break. Don't be afraid to reach out if you need some help. Again, I've updated the Canvas site. So for example, quiz 3 is now available. I've deleted quiz 4 because it wasn't really relevant to us leading up to the Gibbs exam. So there's only quiz 3 now. And remember, the due date now is the Wednesday before we see each other again. Okay, have a good spring break.